Frazzled. Ready for the weekend? Oh, this half's more frazzled than this half. All right. My game plan today is one more concept to tell you real fast on with the liquids chapter, and then you've had several days to. We've had 2 lectures on this in several days. You've been working on your homework that'll be due this weekend. I prepared a few clicker questions to see if you guys are how well you're applying this. And then we'll move to gases. And I got lots of demos on that. And then we'll have a good weekend. So this last principle is nothing new for equations or anything, just a different way to apply it. It's Pascal's principle. Pascal is the unit for pressure. And what is pressure? Yeah, it's a force acting over an area. So just as mass is different than force, force is a mass being accelerated, a force is different than pressure. It's that force acting over an area. Well, Pascal's principle, Blaise Pascal figured this out, that's the unit's named after, that, well, just as your book puts it, a change in pressure at any point in an enclosed fluid at rest is transmitted undiminished to all points in the fluid. All right, how many are thinking? So, I'll give you an idea. A hydraulic jack. I mentioned one of those in the first exam as a type of simple machine question. But let's say you have a piston over here of a certain area, and you have a piston over here of a smaller area, and in here is a fluid, water, brake fluid, even air. The idea is you can exert a force on one side and get a force out on the other, kind of like a lever or a pulley. Well, since that force is acting over an area, you also get a pressure. That force over the area is the pressure. You guys know this. You can lift up your entire car with a hydraulic jack, right? Can you lift up a car by yourself? No. But with a jack, you can. So a hydraulic jack, how's it work? It changes the area. The case here would be like, say you want to push over here with a certain force. Force 1. How will the force compare over here? Let's say you put your car up on the platform. What do you think is going to happen? You hope it'll go up. Let's look at Pascal's principle. If I write it like this, the pressure stays the same in that fluid. That's what he said. It said a change in pressure at any point in the enclosed fluid that's at rest. The fluid in there is not moving. So anywhere in that resting enclosed fluid, if you push on it somewhere, like one side, area 1, that change is transmitted undiminished to every other point in that enclosed fluid at rest. So if you push at A, that pressure is distributed over to A2 without changing. The pressure in there is the same everywhere. It's like if you try to blow into a bottle. I increase the pressure right here, but it's transmitted everywhere in there. So that same pressure is pushing here and here and here and here. That's Pascal's principle. So the pressure in that fluid is being transmitted equally everywhere. And if that's true, and you have a force 1 over here over area 1, what do you get out on the other side? Better be the same ratio. But this area is bigger, isn't it? thus, that's where that bigger force comes. So you get a much bigger force, whoops, out here. And so you only need enough force to push the jack. But you can get a much bigger force over there on your car, enough to actually lift it. If the area increases by a factor of 10, what does the force do? Increases by a factor of 10. Yeah. So see, it's not really, it's not classified as a simple machine, but it's a machine that's multiplying our force. What's it not doing? Simple machines and hydraulic jacks cannot do this. It was on the first exam. Yeah, they can't create energy. See, we're not creating energy. So what has to give here? Well, we're magically getting 10 times more force out just by spreading it over 10 times the area. It seems like, woo! Are we cheating physics? There you go, distance. Who's going to have to move it further? Which side, 1 or 2? 1, yeah. This force, even though it's less, will have to be exerted over 10 times the distance. The work done on this side, work 1, is force 1 times distance 1. Work 2, force 2 times distance 2. So you'll still have less force, more distance, because energy is conserved. But this all worked as an example to talk about Pascal's principle, applying this. You can amplify the force by changing the area because the pressure is equally transmitted throughout this enclosed fluid at rest. That's Pascal's principle. Maybe a less useful way to do it than lifting your car, but maybe a more fun way to do it. Anybody like to go on, take a ride on my hovercraft? Okay, good. Thank you. I'll show you this. Here's the bottom. It's just attached in the middle. You can come on down. Here's the holes. That's where the air is going to come out. And so the idea here is, with just a leaf blower, this exerts a certain amount of pressure. It's loud and it's noisy and it seems like a lot, but I can stop it with my hand. And it's not enough to hold him up, you know that. But if I ask him, go ahead and have a seat on your bottom, crisscross applesauce. We'll try to get in the center of the board. So scoots, there you go. We'll stick it in here. You can hold it. That's the valve. And the air is going to go down underneath and come out the bottom. Yeah. Scoots this way. Move this way a little further. There we go. Try it again. That's good. Whoop. Whoop. Thank you very much. I appreciate it. You see some good inertia there too. He's moving. Things in motion want to stay in motion. I step on the hovercraft and stop it. Well, he keeps going and tips over. Thanks for being a good sport. So the idea is, this isn't much pressure, but if I spread it over a large enough area, I can get more force out, enough to hold him up and help eliminate friction at the same time so you can scooch along. That's just an example. Any questions about that? Okay. Get your clickers out. Let's see if we can apply some more of this. Whoops, wrong button. So as you're logging in, we'll try to apply some of these, but we're going to transition to gases now, which are still fluids. So everything we just discussed about liquids is true for gases. density, buoyancy, pressure, Pascal's principle, and we'll start applying it there. But you already know half of the next chapter, chapter 14, because all this is still true. Now be quiet so you can read this question. So as you're thinking about this question, because I always take longer on the first ones, you know by now. Water pressure at the bottom of a lake depends on this. So does air pressure at the bottom of the atmosphere depends on this. So we're going to start thinking about the air now. We're in that fluid as the gas, and we're at the bottom of it, right? So whatever the answer to this is, it's the same for air in the atmosphere. How are people with logging in? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Most of you are thinking C. A third of you are thinking all of them. All right. Go ahead and discuss this one with your neighbor. That's enough. I'll reopen this one back up. See what they're thinking. If they're thinking the same thing as you, find someone that's not. Convince each other what you're thinking. You can look back at our notes. You can use your textbook. We had a couple equations, one for buoyant force, one for pressure. Actually, we had two for pressure. It was force over area. Remember, we rewrote that in terms of something else, in terms of density. I emphasized that one thing was depth dependent, one thing was volume dependent. What's this one? Does it depend on either of those or all of them? Those are your hints in case you're forgetting where to look. You don't have to just sit there. I'm hoping you don't just sit there and go, I don't remember. Put the pieces together. I've reopened the poll so you can re-vote based on your discussions. It's all quiet now. I'll take that as I should start counting. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. I'm always curious to see how it changes. 0. Meh. Well, we gained a few more. So the A's and B's moved to C and D, and some of the D's moved to C, but not all of them. So it's either all of them or C. Well, it's C. Pressure is depth dependent only. Remember when we replaced mass in terms of density? We got, actually, I should write it back up then. Is that one? We got that pressure was force over area, and then we did a little math by plugging in the weight and the areas, and it came out to be the density times gravity times the height of the fluid above you, or the depth you are underneath it. That's pressure. Density times gravity times height. So pressure is only depth dependent. It doesn't matter how much of it volume-wise is above you. Remember our Pascal vases? They were all different shapes, different sizes. They held different amounts of water, but because they all went to the same level, because they were all at the same depth, they all had the same pressure down there. Another way to think of this, a dam. Not Adam Beehler, but a dam. The holding back water. Sorry, that's my junior high PE teacher thought it was hilarious. For my entire junior high, for 3 years, 7th, 8th, and 9th grade was our junior high. Take and roll. Adam Beehler. Ha ha ha. Yeah, it's hilarious. For 3 years. But anyway. If your dam is 100 feet deep, 100 feet tall, it's holding back 100 feet of water. That could be a little pond or a lake or the entire ocean. But if at the dam where the water's at, it's only 100 feet deep, the pressure at the bottom of the dam is only based on that 100 feet. The pressure exerted on the wall of the dam, it would be exactly the same as if it was the entire ocean that it was stopping, as long as it was still 100 feet at that spot on the dam. Does that make sense? So it's not the volume, it's the depth. Think of it as how much is above you. That's what's pushing on your area. If I just, I want to look at what's atmospheric pressure? The pressure due to the air in the atmosphere. I just look at the air on top of me, pushing down on me. The weight of the water absolutely matters, but the weight of what water? Just above you, not all of it. Remember what, I'll leave it as that. It's just the weight of it pushing on you. Something 2 miles over there, you can think of that. It's not really pushing on me. It's pushing over there. That force is then transmitted through Pascal's principle through the water, and that contributes to the pressure on the sides, because you're also getting pushed on the sides and on the bottom of you. Remember with buoyant force, if I jump in water, forget that. I'm in a fluid, air. I'm in air. Where's the pressure larger on me? Yeah, at the bottom, because it's deeper. It's got more air above it than my head. So the pressure due to atmospheric pressure is a little larger down there than it is up here. What's that difference create? That difference in pressure creates buoyancy. That contributes to the buoyant force. So I actually am feeling a buoyant force. The air is helping buoy me up a little. Am I more dense than the surrounding fluid? Yeah. So I sunk to the bottom, right? How about a helium balloon? It's less dense than the surrounding, and it'll float because it displaces enough air, enough fluid around it to create a large enough buoyant force to counter its weight. And so now the buoyant force upward is greater than its weight, and it floats, it rises up. This would be true if you jumped in a vat of Jell-O too, if you think of it as a fluid, I guess. I don't know. Questions? So what's volume dependent? Buoyancy. It doesn't matter how deep you are. If you take up the same volume, it's the same buoyant force. Because there's that same difference in height, difference in pressure from top to bottom of you. Good. So pressure is depth dependent. Buoyant force is volume dependent. Doesn't care how deep you are. All right. The buoyant force that acts on a 20,000 Newton ship is what? Typical ship, you see it out there in the ocean. or a lake. You pick your ship. Obviously, this is a big one, though. 20,000 newtons. The buoyant force that acts on a 20,000 newton ship. What is it? And again, while you're considering, not to just mess up your thought process, but this is true for a ship in the ocean. It's also true for a blimp, an airship that can float around in the sky. You can think of it floating in the sky, surrounded by its fluid of air around it. They both would have a buoyant force on them. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Guys are still split. But the majority are saying B. The majority has it. Let's discuss why, obviously. Yes, what are you thinking?
But last time didn't we discuss how you said the force of buoyancy is greater than the mass times the acceleration of gravity?
Yeah. Well, for what's instance? If it floats. Right. So if the upward force, the buoyant force, is larger than the downward force, the net force is acting in which direction? Up. So the thing accelerates up and rises to the top. What happens when it gets to the top? The gravity pulls it right back down and it resinks? All right, so how about a typical ship that's just floating on the top of the ocean? It's not going up, nor is it sinking, going down. What's equal? The two forces are equal? You guys don't sound confident. If the weight is more than the buoyant force, whoosh, it does what? Goes down. Remember, the forces don't change. We talked about those the first half of the semester. If this force is bigger than that force, then the net force is down, and this mass must be accelerating down. It'll move down until what happens? It hits the bottom. And now you have a support force from the ocean floor or the bottom of your swimming pool contributing to that upper. And now they're balanced because you're not going up nor down. In this case, you're right in thinking that things float. This is where we get stuck maybe with common layman's terms. We say float. And that means it's floating at the top. But that means it had to rise to get there. On the way up, the buoyant force is bigger than the weight. That's why it went up. As it comes out of the water, what's changing? Gravity doesn't change. It's still there. The buoyant force changes. Why? As it comes out of the water. Yeah, when it's under the water, all of its volume was displacing the water. Remember, buoyant force is volume dependent, so there's more buoyant force. If you come out of the water some, you're not displacing as much water. So the buoyant force decreases until it balances the weight. Yes?
On that line, for example, if you had a helium balloon and you were 10 feet under the water, it would rise through the water and then keep rising in the atmosphere because its buoyant force is greater in both water and...
That's true. A helium balloon starting out under the water is less dense than the surrounding water, so it would accelerate up quite quickly because it's a big buoyant force compared to water. It gets into the air. Well, it's still less dense than the surrounding air, so it would continue going up. Or think of a normal balloon. It's just full of air. You put it underwater. You know it's going to accelerate up and then pop up and then settle on the top like we saw. Only a little bit of it's submerged. That's the amount needed to displace enough water, and the weight of that displaced water is the buoyant force. And now the two forces up and down are balanced. So, for a 20,000 Newton ship, the buoyant force must be 20,000 newtons, or else it would be going up or going down. That'd be true for all objects not going up nor down. So a fish hovering underwater, the buoyant force has to equal the fish's what? Weight. They'd have to be equal, wouldn't they? Now the fish takes on a little more air through its gills and increases air in its swim bladder. What happens? It rises and now has a larger buoyant force, and it starts moving up. Now it lets the air out until and decreases the buoyant force until they're equal, and it hovers over here. Same with a blimp in the air or a submarine underwater. What do we call it when it's just floating there? Neutrally buoyant. That's when the two forces are equal. So anything that's neutrally buoyant, and that can be in the fluid or the transition, like on the surface of water. You know, you just hop on your inner tube, whoosh, you're floating there on the surface. Well, if you're not going up nor down, then the buoyant force on you has to equal your weight. You just don't happen to be completely underwater. You're only displacing enough volume of water to create a buoyant force that equals your weight. Does that help? If this stuff gets confusing, I encourage you to keep processing those homework questions and always look at the answer keys. If you don't understand those by the end, before a test anyway. Also, the textbook has several check your understanding questions throughout it. Remind you of those that are just like these type of questions with the explanations. So after you think about it. Well, let's do another one. Let's take that 20,000 Newton ship, and it's in salt water. It moves into fresh water. What's the buoyant force on the ship now? Some of you might be trying to remember this without looking in your notes, and it may or may not help you. The buoyant force was the density of the fluid, the volume of the displaced fluid, times gravity. So the buoyant force was volume dependent. It also depends on density and gravity, where the pressure was just the depth dependent, and density and gravity. They both depend on density and gravity. So what happens to this ship? It wants to know the buoyant force itself. If you're in salt water versus fresh water. How are we doing? 34 of you have answered? I'll even give you another clue. What's the ship going to do? Anything? You think it'll go up? So it starts out in salt water. Oh, down? Why? Because you know you float more. See, it's good to use your common, you already know that. Why do you float more? And what you mean is float higher in salt water. It's more dense. Yeah, the difference between your density and it is greater, so you float more, float higher. Okay, so the ship, we know as it goes from salt water into fresh water, it's going to sink a little. But it didn't ask that. It asked, what's the buoyant force going to do? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Oh, we're still split. All right, discuss it with your neighbor. Two things are changing, aren't they? My last clue to you. The volume of water being displaced changed because it's deeper in now. But the density is also different because you're in freshwater instead of saltwater. All right, keep talking. Yes? Oh, you can consider it's here. Now it's here. Get rid of the muddy in-between transition. Actually, the answer is true in there too, but it'll help you. It's fine. Clearly, this is a good thought-provoking question. Yeah. Yeah, that's why I always put a subscript there. The Archimedes principle says that the buoyant force is the weight of the displaced fluid. When we replaced the mass with density, it was of the displaced fluid. So it's of the fluid. The density in that formula, I know the lights are dim, is of the fluid, not the object. Well, let's see if anything shifted. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. It did shift quite a bit. You know what? You guys are smarter than you give yourself credit for. You shifted correctly. The majority of you. So, two ways I like to look at this. One, the explanation that the author gives. The ship floats a bit lower in the freshwater. Does everybody understand that at this point? Why it floats a little lower? Okay, so it displaces a little more volume of water. But it'll still displace the same weight of water. It displaces more water because it needs a greater buoyant force in fresh water. Is it still floating on the top? Is it going up or down? No. Which is maybe why you asked about the transition. Look at it over there in fresh water. It's still floating. In the salt water, it was floating. It wasn't coming up out of the water. It wasn't sinking. That means the buoyant force has to equal the weight of the ship, or it'd be going up or down. So if it floats in salt water, they're balanced. If they're floating in glycerin, they're balanced. But how much water you have to displace affects the buoyant force needed to do that balancing. Since fresh water is less dense than salt water, it needs to displace more of it because it's the weight of that displaced fluid that determines the buoyant force, and you need a more buoyant force than in the fresh water. Does that help? Kind of cool, huh? So it's still all about forces balancing or not, net forces. We're just using density and to make the change here. Let's see. We are on. All right. Students love this one. This one can be more confusing. So you got a pail. It's filled to the brim. So you place a boat now in the water. What's going to happen to some of that water in the pail? It's going to spill over, right. So it's not part of the pail and the boat anymore. So how will things adjust?
The water that spills out still on the scale.
The water that spills out is no longer registering on the scale. So you can just think of like a little scale with a little beaker of water here, totally full. Put a boat in, water splashes over. It's no longer being read by the scale.
So does the water in the boat, the water that is displaced, weigh the same amount as the boat?
That's part of this question. What do you think? Do you think the water that's displaced weighs the same as the boat? The boat floats on the top. Did it say that? Water spills. The floating boat. Yes. Good. You know that if the boat's floating, what two forces are balanced? The buoyant force and its weight. Those are balanced. If it's floating on the top. Yep. What creates that buoyant force? Yeah, I'm stretching you. We've had 2 lectures on this. We're moving past the chapter, and I want to make sure you guys are. No, it's floating on the top like a normal ship. The float does not sink. The boat does not sink. What causes the buoyant force upward? What creates that? The what? The weight of the boat determines the buoyant force? The volume displaced? What's Archimedes' principle? Look in your notes. I heard it here. Archimedes' principle says the buoyant force is the weight of the displaced fluid. It's based on how much of the fluid you displace. When you put the boat in the water, it displaces fluid. It flows over. We did that. Remember, I submerged the cylinder over here in water and it spilled water out. And then I weighed that water and showed you that the weight of that displaced water was equal to the buoyant force. Have I given you enough hints? Should I just get to the answer now?
Just assuming, if you were to put like a lead brick in just like a little bit of water, there's no way that the water displaced weighs the same as the lead brick.
I would agree with that. I would agree. Hence, the lead brick does what? Sinks. So yeah, I'm just repeating for the camera. If you put a lead brick in a little bit of water, it displaces water, but it can never displace enough to create a buoyant force as large as its weight, because it's really dense. Right. The lead, if you could spread the lead out, so essentially you're creating a lead boat, right? Well, now you've increased the space in there. And that's how they make a ship. That's how you can make a ship float made out of steel. Similar question. Then it could float. But it's the density of the boat then, not just the material it's made out of. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Whoa, all right. Most of you. Very good. I'm impressed. So the idea there, for those of you that didn't come around, it displaces water falls over. It displaces the exact volume that it's submerged. If we weigh that, that's the buoyant force. Well, that just left the scale, so the scale goes down by buoyant force amount. But the boat's now in there. And it's being supported by the water by an upward buoyant force, right? So Newton's third law, for every action there's an equal and opposite reaction. So the water pushes up on the toy boat to keep it up. The boat is pushing down with that same buoyant force onto the scale. And so it comes right back to the same reading. The water overflowed, but that was the same weight as the boat. It was just like that demo. The weight went down 1.5 newtons, if you remember. That was when the water left. At the same time we put it underwater. But when I put that water right back in, it came right back to where it started. That's due to the buoyant force. All right. Let's see. A few demos to end out with here. Didn't get through all, and that's okay. We learned a lot. Let's do the ones I don't feel like setting up again. This one. It's a great way to go out. Here's a ping pong ball. It bounces. It's normal. Nothing special about it. Boink. It's on the end there. I'm going to seal the ends of the tube with this highly technical packing tape. It's just packaging tape. Push it on. I want a good seal. Put some pop cans in front of it. I'm going to do the same thing over here and seal this end off. Make sure it's a good seal. Because I have a vacuum pump on the floor over here. And I'm going to start pulling some air out of the tube. All right, the ball's right here. What's in front of it? Not anymore. A lot less air. The pressure in there is less than it is out here. Air has pressure. It's a fluid. There's less pressure from this air than there is from water because it's less dense. But there's a lot of atmosphere. It does create pressure. So what I'm going to do is take this knife and rupture the tape on this end. What do you think the air in the room will do? Well, yeah, high pressure moves to low pressure. What's in its way? The ball. So it's going to exert a pressure over an area. That creates a force. Pressure times area is force. That will accelerate the ball. You ready? 1, 2, 3. There's the first can. The ping pong ball went clear through the first can. Let's see what it did to the second can. Oh, it made it through the second one too. Yeah, all right. Good day. Here, maybe since y'all can't see. Went through that one. Third can. Nope, it didn't go through that one. Those of you that are disappointed, she's not. That's why we do 3 cans, so it stops it. But it did dent it. Here's what's left of the ball. So we've clocked this ball. It was going over 500 miles an hour. That's 75% the speed of sound. Yeah?
Just because you just said that, I think, I was going to ask if it would go through your hand.
Would it go through your hand?
John wants to try. No.
No. Do you want to try it?
No.
Yeah, I wouldn't either. There's actually a professor, a colleague of mine I know that teaches at BYU, and he would take it point blank. He'd stand there in front of it like this. And he did that for many years. He would do it for his class. Oh, yeah. He doesn't do it anymore. Because, yes, he confessed that he'll get a welt, a big welt, for several weeks. Yes, it hurts. Clearly, it's packing enough wallop, momentum, energy, to go through 2 pop cans. So, yes, it would hurt. But it wouldn't go through your hand, probably. I'm not going to find out. Yeah, if I removed the first 2 cans, actually somebody did this Wednesday in a different class. It went through the first can. He didn't think it was enough, so he removed it. Actually, I don't know if he removed it. It doesn't matter. There's a hole through it now. He did it again. It went right through the first can without stopping, went through the next 2 cans, and came out. So it was a little dangerous. He shouldn't have done that. I wanted to see what would happen, so I took this and aimed it like this. I wanted to see if it would break on the back wall. What do you think happened? Wow, the room was empty. Just me and a friend. I was curious because a ping pong ball is really light. So I knew air resistance was going to be a big factor, and I wanted to know, would it slow down quickly enough? Because it's coming out fast. But would it slow down enough to reach the back wall? I wasn't sure. I made a guess and went for it. Well, it smacked the back wall pretty good. But it did not break the ball. So it slowed down enough that it wouldn't have hurt if it hit you. But it was going fast enough that air resistance didn't. There wasn't enough air in the room to slow it down enough. So it wouldn't have gone through a pop can or anything. So to end with, atmospheric pressure. Do you guys know what the value is? That's close. It's 14.7. So 15 pounds per square inch, because pressure is over an area. I'll just end with this, and we'll continue more of this stuff next week. But imagine a 15-pound quarter. Put it on your arm. Ooh. Now, take a second 15-pound quarter and put it right next to the first one. Ooh. Cover your entire body with 15-pound quarters, because there's 15 pounds acting on every square inch of your body. That's atmospheric pressure. All the air above us, the weight, it works out to be 15 pounds on every square inch. So next time you're feeling down or depressed, think of that. You're withstanding. That's what you're feeling right now. Why aren't you just being crushed? Because you're balancing that back, your bones and your muscles. You're strong. So go with that. Remember that this weekend, and I'll see you Monday.